Welcome students to another session. Let us see some more concepts in this class. Now let us say I take a radioactive sample. I take a radioactive sample. Now this sample, let us say some sample is there. In this, there are 100 nuclei are present, and as per the natural process of this radioactivity, these are decaying. Now after some time, this 100 became 100 by E numbers. This is 100 numbers and this is 100 by E numbers. It must have taken some time, T. So if I consider the reciprocal of this time, now that is called decay constant. Okay, decay constant. So here, this is the original number, this is the leftover number now. So decay constant means, so this is the original number when it becomes 1. Original was, let us say, 1. So 1 upon E of the original number should be remaining now. It must have taken some time. The reciprocal of that time is decay constant. So from 100 to 100 by E, 100 numbers became 100 by E. What is the value of E? 2.71. So 100 divided by 2.71, let us say. You get some number over here. How much? Let me calculate. 2.7, no? Let me just... $36.9. Original was this, now remaining are this. It must have taken some time. Let us say 5 seconds. Alright, so what is decay constant? 1 upon 5. Now, this radioactive process, if you understand, see, radioactive process is happening naturally. Alright, there is a big nucleus which is breaking down. Okay, it is breaking down so that the bigger nucleus is breaking into smaller nucleus so that it gains stability. Now this some process is happening here. So this process is independent of you are putting some external process. You are trying to influence this pressure, temperature, chemical process. Nothing is going to influence this. This external process, anything you take, pressure, temperature, chemical reactions, anything, it will not influence this radioactive process. Now this process is what? Radioactive process. Okay, you need to understand this. It happens itself. It happens itself. Okay, it's a property. So note this. Now this decay constant, what we have been talking about, it depends upon the type of sample. Whether it is uranium, whether it is thorium, whether it is bismuth, whether it is lead, it depends upon that. Okay. So in the previous class, the decay law we have seen. Decay law, let me just again write it. N is equal to N0 into E power minus lambda T. Now this is the decay constant. What is this? N, number of nuclei leftover. What is N0? Original number. I gave an example also that original number was 100. Let us say 20 decay. So what is the leftover number now? 80. So this is your N and this is your N0. Now this 80 became another 20 got decayed. 80 became 60. So what is the present N? This. What is N0? It is this only. N0 is not going to change. What is changing? N is changing. Okay. Now here we will talk about a concept called half-life period. Half-life period. Okay. Let us first understand this. Let us say we take a sample. In that sample, some 10,000 nuclei are there. Now this 10,000 became, I took a particular sample in which 10,000 nuclei are present. 10,000 became 5,000. What happened? Number became half. Some time it would have taken. That is denoted by T half. So that is called half-life period. Now this 5,000 became 2,500. Some time would have taken. That is also T half only. Is this and this different? No. It's not different. Okay. So when you talk about half-life period, so you can take the starting number, you can take the middle numbers, or you can take the last numbers also. The T half concept remains the same. So we have to calculate this T half. So how to make the calculation means, see, even this number may not be the original present number. Original number may be 10 lakhs, isn't it? So 10 lakhs may become 5 lakhs, 5 lakhs, 2.5 lakhs, 2.5, 1.25, and this process can keep on continuing for a very, very long amount of time. So this was the equation which we have derived for radioactive decay law. This is the radioactive decay law. Now we are saying that after some time this N0 is becoming N0 by 2. So that means N0 by 2 will be remaining. N0 was the number, let us say 100, 50 got decayed. How many remaining? 50 remaining. So what is N0 by 2? So this N0 by 2, this becomes N0 by 2, N0 e power minus lambda into this time we are saying defining as T half. Alright? So cancel this. Half is equal to e power minus lambda into T half. Apply logarithms both sides with base e. This is ln1 minus ln2 is equal to minus lambda T half into ln e. Ln e value is 1, So this becomes ln1 is 0. This minus minus goes off. ln2, the value of logarithm of 2 with base e is 0.693. Alright. So 0.693 by lambda is your T half. Let me a little bit tilt this screen so that you are able to see. So this is the expression for T half. This is the expression for T half, and T half is dependent upon, you can directly see the lambda value. So it is dependent upon the sample. Is it dependent upon the sample size? No, it is dependent upon the sample type. You're talking about uranium, or you're talking about lead, you're talking about thorium, you're talking about bismuth, or you're talking about iron. Is iron radioactive? Iron is not radioactive. We were discussing that binding energy curve. That curve was something like this, like this it was going, The peak value was for iron. Iron is very, very stable. Iron is very, very stable. No need for it to get decay. It's Binding energy also is very high. This is not radioactive. If this was radioactive, we wouldn't construct our houses with this iron and all these things, because all these radioactive nucleus, they emit particles which are radioactive in nature. They can penetrate into your cells, body cells, and they can damage. So we have to be very careful. This is a nuclear reaction which is happening. So, you know, so we are not talking about nucleus such as iron and all those. We are talking about the larger nucleus, the one which are greater than usually 220. A value greater than 220. Such type of nucleus we are talking about. So here different elements are there. So different element will have different lambda value, and this T half value is dependent upon that. And if you see, actually the range of T half is sometimes as small as 10 power minus 16 seconds to as large as 10 power 9 years. 10 power 9 years. This is the range. This is the range. This is nothing. Very fast it is decaying. It is very slow. This is a very slow process. 10 power 9 years. We have to check whether it is the age of the earth. So from the formation of the earth it is happening. But this is very quick. Okay. So it is 1 upon T half is proportional to 1 upon lambda. So if lambda value is very high, what will happen? T half will be very less. Okay. So this is one thing you have to understand. As an example, you can see here uranium with atomic number 92, mass number 238. It has got 4.47 into 10 power 9 years of T half time period, whereas krypton is only 3.16 minutes. Okay, just to show you an example, I have shown this. Now let's talk about one more point here. Now sometimes what happens is you have a radioactive element X and it is decaying and becoming into some other nucleus, let us say Y. Alright, this is the process of decay. Now you are calling this as parent and you are calling this as daughter. Now why it is not son and all this, let us not get into that. Parent, daughter. Now this is a sample basically. X is a particular type of radioactive substance. It is a sample. You took the sample of 1000. In this 1000, some are decaying into and becoming into Y. Some are decaying and becoming into Z. Can this happen? It can happen. Alright. So this is called parallel decay. Parallel decay. Okay. Now here, this process can have a decay constant of lambda 1 and this can have a decay constant of lambda 2. So here what we do is we calculate the effective decay constant. So it is given by lambda 1 plus lambda 2. Suppose another 3 4 happening, lambda 1 plus lambda 2 plus lambda 3 plus lambda 4, like that. So one more thing we need to understand is, suppose you took a sample which has got 1000 nuclei, alright, or let us say 100 nuclei. Took a sample which has got 100 nuclei. Now in this 100, 30 became 1. Obviously 70 will become Z, isn't it? Either it can undergo the process of becoming into Y or Z. There is no other third party. So you can say that there are 30% chances, 30% chances of this X becoming Y and 70% chances of X becoming Z. So we can write lambda 1 as lambda effective into probability of 1. Okay, it is probability here 30 by 100. Okay, and lambda 2 is lambda effective into probability of 2 happening. Alright, So here 70% chances are there. If you write it as a fraction, it is 7 divided by 10. Okay. So this is also one concept you should know. Okay, let us understand one more concept. Let us say some radioactive element A is there, some sample you have taken. It is decaying and becoming B. Now B decaying, becoming C. C decaying and becoming D. Is it possible? It is possible. Here the thing is happening in a sequential way. Parent, daughter. Again this became parent, daughter. Now this became parent, daughter. See students, this is not we are kind of playing a mathematical puzzle. It's not like that. It is happening in nature. Okay, it is happening in nature, and the substance has to be radioactive in nature. It's not, we do not, it is not like we will put in mathematically and we cannot break our stable atoms like this. We're talking about unstable atoms. Unstable atoms means unstable nucleus basically. What is atom? Atom is basically consisting of nucleus. That nucleus can be stable or unstable, so that it itself makes the atom stable or unstable. Now one example I have shown you. This is radon. What is this? Alpha particle. Any radioactive process which happens, it emits alpha, beta or gamma radiation. Alright, either it emits a alpha particle is helium nucleus, beta particle is basically a fast moving electron. Beta particle that we have discussed in the previous videos. See dear students, all these videos are kept in that playlist. I would request you to go to that playlist. There are 3-4 playlists are there. Mechanics is there, electromagnetic, whatever little bit contribution I have done. Conceptual videos I have put over there. You can go and watch over there. Alright. I'm not telling all this. Our link is given here. Is that it is there in the playlist? Kindly go there and see. Now coming to the point. Here I have taken an example. This is radon. Alright. Helium is released. What will happen? 2 charges has to be balanced. 86, 2, then it will be 84. What is this basically? Number of protons, isn't it? So this is 220, this is 4, so this has to be 216. Luckily we have another, I think this is polonium. My knowledge about chemistry is little halka pulka. Polonium, right? Now again, this is undergoing a decomposition. This is undergoing a decay, not decomposition. So 84, again it is breaking and giving a helium nucleus. So 82, 216 minus 4, 212, it is lead. Now again it is undergoing a radioactive process. Lead 82. Here what is this? This is a beta particle. This is a beta particle. So what will happen? This will increase by 1, I told you. Remember? One neutron will become proton. And this will remain as it is. Okay? So what is this? Bismuth. Bismuth. So again a helium nucleus is released. Then 83, 83 minus 2, 81, 212 minus 4, 208. Again luckily one more element is there, which is thorium. So this is happening in a sequential way. You can call it series maybe. Okay. So this also happens, So this is different from the one which we were talking earlier. The one which we were talking earlier was, this is X is becoming Y and X is becoming Z. So this is a parallel process. So, out of a sample of 1000, maybe 700 are becoming Y and 300 are becoming Z. They're not waiting for any permission, right? So it is a parallel process. This is not a parallel process. This is a series process, sequential process. So kindly note down. See, often this half-life period, this type of questions come. Half-life period. What is this basically? So T half you have written as 0.693 divided by lambda. What is this 0.693? It is ln2 value. You can also write 0.693 divided by lambda. So half-life period means how much it will be? So it is let T prime. It will be 0.693 by lambda into 1 by 2. How much is it? Let me do little tick tick in the calculator. Tick 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 tick. 0.346 465 lambda. Alright. So we'll do one thing. Let us take a radioactive sample which has got 1000 nuclei. Alright. Now our equation was n is equal to n0 e power minus lambda into t. Isn't it? Now which time we are talking about? We are talking about half-life period. So this was the half-life period. So half of half will be this much. So this is the value of t now. So we need to write over here n is equal to n0 into e power minus lambda multiplied by 0.3465 divided by lambda. Alright. But what was n0 we have taken? N0 we have taken as 1000. So this is e power minus 3465. Let me make the calculation. Why we are doing this? So why not you are taking 1/4 of half? Usually questions are asked on this. That's what we are doing. Alright. So 3465. It is 1.414, which is root 2. So it is 1000 divided by 1.414. What is this n? This is a leftover. Let me just do it. 1000 divided by 1.414. It is 707.2. I will take 707. So n value are getting as 707. So how many decade? The number of decade would be 1000 minus 707, which is 293. Or approximately 29.3%. Alright. So when you talk about half of half-life period, 29.3% decay. Leftover, how much? 70.7%. So many times questions are asked on this. You can remember this, you can do it like this. It's up to you. Okay. See, if you try to understand this graphically, if you draw a graph between n by n0 versus time on the x-axis, time is the independent axis, n by n0 is the dependent axis. Alright, so this depends upon this actually. So the graph will be dying down exponentially, and if you observe some specific values over here, so it becomes half after one time period. So n by n0 is becoming 0.5. So at t. So that means n must be n0 by 2. Similarly, now this is leftover. Now leftover is n0 by 4, that is 0.25. So it happens at 2t. So 3t corresponds to n0 by 8. 4t corresponds to n0 by 16. This is the specific values you can remember, which can be very useful to you while doing any numericals or any question comes on this shape of the graph. It is like this. Make a note of this point. So that's it for today, and we'll see some more concepts in the next session. Thank you for your time. Take care. Bye bye.